In a massive multiplayer gaming environment, a leaderboard constantly processes thousands of concurrent player actions every single second. Production environments require two specific guarantees. The system must execute both score updates and relative rank queries in exactly O log n time. Balanced search trees handle insertions efficiently using node pointers, but they cannot dynamically calculate rank. Finding a position requires an in-order traversal, illuminating and physically counting every preceding node. This linear scan drops performance down to ON. When millions of active players trigger an ON operation simultaneously, the resulting CPU spike can completely crash the entire server instance. A single standard data structure cannot provide both rapid lookups and fast relative ranking. To solve this, production systems use a dual-structure code design. An in-memory hash map maps player IDs to absolute memory addresses. Instead of a top-down tree search, the system snaps instantly to the correct internal node. It then uses parent pointers to traverse upward, adjusting tree metadata. The updated node is then detached and spliced into its new sorted position within the tree hierarchy. While lookups and updates are now optimized, the linear O of n rank query problem remains. Bypassing searches with a hash map is only half the battle. To support fast ranking, the ordered structure itself must be modified. The only way to bypass linear traversals is through data structure augmentation. Here is a self-balanced order statistic tree, or SBOST. We've added a size metadata field storing the total nodes in a subtree. As players join, these fields update. During traversal, the system calculates rank by summing leftingless subtree sizes, jumping over thousands of nodes instantly. This mathematical shortcut eliminates the need to scan and count individual elements. By trading a small amount of memory to store these size fields, augmentation transforms the O of n rank query into an O of log n calculation. High-frequency production environments are chaotic, involving thousands of concurrent data mutations happening in just a fraction of a second. Deterministic balancing in trees, like red-black rules, requires rigid structural rotations to guarantee O of log n height. A single rotation alters multiple parent and child pointers simultaneously. To do this safely in a multi-threaded environment, the system must apply a red lock barrier, blocking incoming updates. These mutual exclusion locks create a severe traffic jam, where threads wait on structural changes instead of processing player scores. Deterministic tree rebalancing creates a concurrency bottleneck that limits write throughput regardless of hardware. To solve the lock bottleneck, systems like Redis DZ use the skip list. This is a skip list, a multi-level linked list driven by probability rather than deterministic rules. A newly inserted node is assigned its vertical level height based on simulated coin flips. This probabilistic height distribution guarantees O log n search times without ever requiring a global rotation. Pointer updates in a skip list are strictly local to the inserted node. Because changes are local, multiple threads can update different sections of the list simultaneously without triggering a global lock. But this raises a question. How does a flat skip list calculate rank without the subtree sizes found in a tree? This shows the skip list's augmentation, the span counter. Every forward pointer has a distinct span integer value assigned to it. A node's rank is calculated by summing the span distances jumped during a level 0 traversal. By replacing deterministic trees with probabilistic lists, architects achieve O log n ranking while enabling lock-free concurrency. The combination of a hash map and an augmented skip list is a robust solution for player-centric indexing. However, this architecture hits a hardware wall when scaling to tens of millions of concurrent connections. Storing hash map references, arrays of multi-level pointers, and span metadata for 100 million distinct objects eventually exhausts RAM. When engineering for planetary scale load, maintaining a one-to-one node-to-player ratio becomes a hardware liability. Scaling past this point requires a move from player-centric indexing to score-centric indexing. This approach requires the application to operate within a bounded, discrete range of possible scores. This diagram shows the Fenwick tree, also known as the binary index tree. The x-axis strictly maps to the available score range. Each index represents a specific score. The integer stored inside is the frequency, representing the volume of players holding that exact score. Indexing the scores instead of the players eliminates individual object overhead and the need for complex pointer arrays. The Fenwick tree executes prefix sum queries to find rank using bitwise operations, specifically x and -x. This diagram shows a rank query. These bitwise operations allow the algorithm to make least significant bit jumps, summing frequency ranges in exactly O of log s max time. Performance is now strictly bound by the maximum score limit, not the player population size. In this model, calculating the rank for 10 players takes the exact same computational effort as calculating it for 10 billion players. Engineering for this volume isn't about building denser data structures to hold more users. It's about shifting the mathematical index so the total user count no longer matters.